Hello guys, welcome to CFD College. I'm Ashkan, and in this video I'm going to solve some questions from chapter 3 of Fluid Mechanics 1, the book which is written by Manson. In this video we are continuing solving assignment C from the course Fluid Mechanics 1. Presented in Concordia University, but I think these tutorials, solving these examples and problems can be useful for anyone. So if you would like to see such these videos, you can check my previous tutorials on Fluid Mechanics 1 in the playlist. And if you are interested in CFD and sysfluent pre-processing, post-processing, and computational fluid dynamics, we have lots of useful videos on the YouTube channel that you can watch and enjoy. Okay, let's start this session. As I mentioned in this tutorial, I'm going to solve some problems from chapter 3 of Fluid Mechanics 1, when we should use Bernoulli equation. When we have a fluid flow, most of the time in Fluid Mechanics 1 we should use Bernoulli equation. You will see we have other types of Bernoulli equation. We call them energy equation. We called it energy equation, and we will deal with that in future chapters. But in this chapter, we should work with Bernoulli equation. Bernoulli equation, when you want to use it, you should know that there are some assumptions to use this equation. The first is we should have inviscid flow or steady flow. I think the first one should be a steady flow. Second one is inviscid flow. And the third one is incompressible flow. So you should always check these assumptions, and then you can use Bernoulli equation, which is P over gamma plus V2 over 2G plus Z equals constant, a constant value. Gamma is rho G, so we have other forms for this Bernoulli equation. For example, if you multiply the equation by, for example, G, we will have pressure over density plus V2 over 2 plus plus GZ equals another constant value. And you can also multiply the general form by gamma. So in that case, you will have P pressure plus rho V square over 2 plus gamma Z equals another constant value. So we have different types of Bernoulli equation, but we usually work with this one. Okay, let's solve the first problem number 33 of chapter 3. Here you can see a building, and water flows from the faucet on the first floor, so here, of the building, shown in the figure below, with a maximum velocity of 20 feet per second. So here we have the inlet of the water, and here is the first floor, here is the second floor, and here is the basement. And we know the velocity at this exit is 20 feet per second. We have steady inviscid flow, and since we are talking about water is incompressible, so the third assumption is true in this problem. Determine the maximum water velocity from the basement facet and from the facet on the second floor. Assume each floor is 12 feet tall. So here is 12 feet, and we know here is 4 feet, and so this distance, this height, should be 8 feet. So if we consider the axis like this is the axis. Here here we have Z1, here we have Z2, and here, for example, okay, so let me use these numbers. Z1 here at the basement, at the first floor, Z2 at the basement, and Z3 on the second floor. So Z1 equals 4 feet, Z2 equals minus 8 feet. The total height is 12, and here we have 4 feet. So this height is 8 feet. And Z3, from here up to here, we have a floor, total floor 12, and we have 4 feet here. So Z3 equals 16 feet. It's not difficult. You can calculate the values. When you want to use Bernoulli equation, you should find key points, key sections, where on these key points you should have some info on pressure, velocity, or the elevation. So, for example, at point 1, here we know the pressure, the elevation, and the velocity. At point 2, we know the pressure and we know the elevation, but we want to find velocity. And the same goes for point 3. We know the pressure and the elevation, and we want to find velocity. So we should select 2 points, and between them we can use Bernoulli equation. On point 1, we know everything at point 1. So we start from point 1 and go towards point 2. So between point 1 and point 2, we should write Bernoulli equation. Okay, let me change the color. Between point 1 and point 2, we should write down Bernoulli equation. P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. What do we know? We know that V1 is 20 feet per second, Z1 is 4 feet, Z2 is minus 8 feet, and P1 at point 1 and point 2 at the exit, we have atmosphere, so we have atmospheric pressure. And you know, in fluid mechanics 1, we always work with gauge pressure unless it is specified. For example, if we are told that the pressure is, for example, 12 psi absolute, or for example 10 to the power 4 Pascal absolute, it means that the pressure, we should work with absolute pressure. But in general, we work with gauge pressure. So here at point 1, 2, and 3, we have atmospheric pressure. So pressure at point 1 and at point B and also at point 3 is equal to 0. So now it's easy. This term is 0, this term is 0, and we have the other values. So V1, which is 20 feet per second square, divided by 2 times gravity, 32.2 feet per second square, plus Z1, 4 feet, equals V2 square divided by 2G, 2 times 32.2 feet per second square, plus minus 8 feet. And from this equation, you have everything. You can find V2. So V2 equals 34.2 feet per second. And for point 3, we should write Bernoulli equation between point 1 and 3 or 2 and 3. Now you know the velocity at point 2, so you can use Bernoulli equation between point 2 and 3. But between point 1, 2, and 3, we know P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. And what do we know? We know that P1 equals P3. Oh, I'm sorry, all these are 3, not 2. So P3 over gamma and Z3 and V3 square. P1 equals P3 equals 0. We know Z1 is 4 feet. Z3 is 16 feet. And we have V1, which is 20 feet per second. So these terms are cancelled, and we can find velocity just like previous part. So 20 feet per second square over 2 times 32.2 feet per second square plus 4 feet equals v free square divided by 2 times gravity plus 16 feet. And from this equation you can find velocity, and it's not difficult, as you can see. The first term, this term equals 6.21 feet plus 4 feet minus 16 feet equals v free square over 64.4 feet per second square. And if you calculate this, it's a negative value. It's 6.21 plus 4 minus 16. So here we'll have minus 5.79. So it means that v free square equals a negative value, which is not possible. It means that with this system we cannot pump water to the second floor, so we need to have a pump. So it's a trick. It's a tricky problem, but it's not difficult. If you know the math, you can easily understand it. Okay, let's go to next problem. Problem number 45. We have a fluid flow inside this pipe. The pipe has the diameter of 0.75 inches. Here is the outlet, and we know that the water rises up to 2.8 inches above the outlet, and we want to know the flow rate of the water. Okay, so what should we do? We should first identify 2 key points. Then we can use Bernoulli equation. So let's examine different points. We have 3 points here, here, and here. For this point, as you know, we have velocity, because here velocity of the fluid is 0. So we have velocity, we have pressure, and we have the elevation. So this is one of our key points. So this is point 2. This point, at this point, we know the pressure, because here at the exit we have atmosphere, so we have pressure. We don't know the velocity, and we know the elevation. If we put axis here we'll have z, for example. If it's the first point, z1 is 0. What about this point, the third candidate? Here we know nothing. We don't know the pressure, we don't know the velocity, and we don't know the elevation. So we identified our key points, point 1 and point 2. So we should use Bernoulli equation between point 1 and point 2. P1 over gamma plus V1 square over 2g plus Z1 equals P2 over gamma plus V2 square over 2g plus z2. Okay, what do we know? We know that v2 is 0 at this point 2. We know z1 is 0 and z2 is 2.8 inches. We also know that P1 equals P2. We have atmosphere there and they are equal to 0. So this term is 0, this term is 0, this term is 0, and this term is 0. We only have these terms, v1 square over 2g and z2. So v1 square over 2g equals z2. So you can find v1, it's equal to a square root of 2gz2. So you should put the numbers 2. Gravity is 32.2 feet per second square, and velocity we don't, and z2, which is 2.8, but it's in inches, so you have to divide it by 12 to have the value in feet. So v1 can be found as 3.88 feet per second, but we want to know the flow rate. Flow rate Q is equal to V times area, velocity times area. We know V1, which is 3.88 feet per second, and we know the area. The area is pi divided by 4 times diameter, 0.75 over 12, because we need it in feet, and a square. So from this equation you can find the flow rate, 0.011119 cubic feet per second. So see, these equations, these problems, are not difficult. The Bernoulli equation is really simple. Let's go to the next problem. Third problem number 59 of chapter 3. Here we have a pipe contraction. As you can see, we have a pipe contraction. For a given 0.2 meter difference in the manometer level, determine the flow rate as a function of diameter of the small pipe. So here we have a manometer. The difference is 0.2. D is the diameter of the small pipe, and we want to find the flow rate as a function of this diameter. Okay, first step is to find our key points. When you have these manometers, you can use these manometers to identify the key points. It's easy. One of them is here at the entrance of the second manometer and of this manometer, and the other point is here, right beneath of this manometer. So here is point 1 and here is point 2. So we have our two key points using the manometers. So it's easy now. We have to write down the Bernoulli equation between point 1 and point 2, P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. Okay, what do we know? We know that the elevation is constant between point 1 and point 2 because the pipe is horizontal. So z1 equals z2. But what about pressure or velocity? You can see here we have two different types of manometers. This is the first one. Okay, it's A, not 1. And this is the second type. As you can see here, this type, the second type, B, it has an entrance inside the pipe while it is connected to the edge of the pipe, to the wall, to the surface of the pipe. So what is the difference between these two types? Using manometer type A, we can find static pressure or static head. While using B manometer, we can find and determine dynamic pressure or dynamic head. When we use this type of Bernoulli equation, if you can see, okay, let me write down it here, P over gamma plus V square over 2G plus Z equals constant. If you pay attention, all the units, the unit of these terms is feet. We call these terms a head. This is pressure head, this is velocity head. So this type gives us the head, or it's better to say that we use the heads in this type. But in another type, P plus rho V2 over 2, here I should use the square, plus gamma Z equals a constant. Here we have pressure, and this is static pressure, this is dynamic, this is velocity, and the combination of first two terms, P plus rho V square over 2, it is called dynamic pressure. The summation of static pressure and the dynamic and the velocity term. So let's get back to our problem. So using manometer type A, we can find static head, and using type B, we can find dynamic head. So from this one, we know that, for example, if this height is X, this one from A, we can understand that P1 over gamma equals X, and from this manometer we can find out that P2 over gamma plus V2 square over 2G equals, here is X and here is 0.2, X plus 0.2 meters. That's the difference between dynamic head and static head. Okay, now we can solve the problem. This term is 0, and as well as this term, and we know the value. So instead of P1 over gamma, I can write down X plus v1 square over 2g equals, and instead of these terms I can write down x plus 0.2 meters. So v1 square over 2g equals 0.2 meters. So v1 can be found as square root of 2g times 0.2 meters equals 1.98 meters per second. So we can find the flow rate now. A times velocity. So if we use point A, Q can be found as A1 V1 equals pi over 4. We know the diameter, which is 0.1 meters square times velocity 1.98 meters per second. So flow rate is equal to 0.0156 meters per cubic meter per second for any d. It means that it is not dependent to diameter. It's independent. And I think this one is a tricky problem again. Okay, next problem. Problem number 88 of chapter 3 of Manson of fluid mechanics, written by Manson. What do we have? Water flows steadily. This is a key point. This is a keyword, sorry, not key point. Keyword for you to understand that you have to use Bernoulli equation. Water flows steadily downward in the pipe shown in the figure below with negligible losses. Negligible losses. In which it flow means we don't flow, that we don't have any losses in that. So negligible losses means that you can use Bernoulli equation. And what should we find? Flow rate. We should find the flow rate. Okay, the first step. What is the first step? The first step is to find key points. We know here we have opening and opening. So this is where we have, atmospheric pressure, and you can see that we have two manometers and we have to use them for calculating pressure, and both of them can give us static pressure, not dynamic head. Now you know why, but we have to select key points. One of them is here, without any doubt. It's in front of the, I'm a terrible drawer. It's in front of this manometer, and it's close to the exit somehow. And the other one should be here in front of this manometer. As I mentioned, when you have manometers, use them to find your key points. So this is point 1 and this is point 2, and always go with the flow, guys. The flow is downward, so name this point the first point, point 1, and this one the second point. Always follow the flow. Okay, now we know our key points, so we should use Bernoulli equation from point 1 to point 2. P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. What do we have? We know the elevation difference between point 1 and point 2. So Z1 minus Z2 equals 2 meters. So it's good. Now we know what should we do with 2 terms, and we have other 4 terms. So let's find pressure. Okay, P1, we can use this manometer to find P1. P1, this is point 1, this is the exit, and from point 1 to the exit, you see that here we have atmospheric pressure. Since we are working with gauge pressure, the pressure at this point is 0. Then to reach point A, we should go downward, so we should add this pressure. It means that P1 equals let me write it another way. Here, for example, is point A, and here is point B. So P1, PA, then I go downward, plus, so I should add the pressure, gamma times 1.5 meters equals P1. I reach point 1. So P1 equals gamma times 1.5 meters. Let's find pressure at point 2. So start from point B. As you know, PA equals PB equals 0. So it's point B. I should go downward. I should go downward until I reach the point 2, but here we have oil. It's important. Here we have oil, and here we have water. Okay, so first oil part, the movement is downward, so I should add the pressure, gamma of oil times 1.5 meters. Then we should keep going downward, plus gamma of water times 2 meters, and then I reach point 2. So P2 equals gamma times 2 meters plus gamma of oil times 1.5 meters. Now we have pressures. So we know P1, we know P2, we know Z1 and Z2. We have to think about velocity, because now we have 2 unknown, V1 and V2, but we have only one equation, so we should have only one unknown. Okay, what can we do? We should use in fluid mechanics we usually use continuity equation, which means that the flow rate is constant. So V1A1 equals V2A2, and we know the diameters, so we should use it, I think. V1 times A1 pi over 4 times 1.2 meters square equals V2 times the area pi over 4 1 meter square. So we know that from this equation, V1 equals 0.694 V2. Now we have everything, and we can solve the Bernoulli equation to find the velocity. So P2, let me change this a bit. Okay, P2 minus P1 over gamma equals, we know P2 and P1, which is gamma times 2 meters plus gamma of oil times 1.5 meters minus gamma times 1.5 meters divided by gamma. Oil has the specific gravity of 0.7, so instead of gamma of oil I can write down gamma times 0.7. Okay, so if you solve this, we will have 1.55 meters, because all the gammas cancel out with each other. Now we can use Bernoulli equation. You know, okay, I have to move it to take it to the right hand side. So Z1 minus Z2 equals, this is the easiest part, divided by gamma plus V2 square over 2G minus V1 square over 2G, and you should put this value instead of V1, you should replace it. So 2 meters equals 1.55 meters plus, if we factor out V2 square over 2G, V2 square over 2, and G is 9.81 meters per second square, we will have 1 minus 0.694 square, and from this you can find V2, 4.13 meters per second. And now you can calculate the flow rate. So Q equals A2V2, both, pi over 4 times 1 meter square, and the velocity, meters per second. So the flow rate equals 3.24 cubic meters per second. I think it's okay. Now we can jump to the next problem. Let's have a look at next problem number 92 of chapter 3. Here, as you can see, we have a pressurized tank. When you have an open tank like this with a fluid inside, the pressure on the surface, on the free surface, is 0 or 1 atmosphere, because we have air here. But in these cases, when we have pressurized tanks, when we have a pressurized tank or closed tank. We can call them closed tank. We have a pressure gauge here, and here is the free surface. The pressure on the free surface, on the surface of the fluid, is equal to the pressure of pressure which is shown by pressure gauge. Okay, here we have a pressurized tank. Here we have air, gasoline, and salt water. We want to find P1 in order to have a flow rate of 0.09 cubic feet per second from the tank here. So this is the exit. We know the flow rate, and we want to find the pressure of the air. Okay, first step is to find key points, and as I mentioned, always follow the flow. So the fluid flows in this direction, so I number the points in this direction. In such cases where you have different fluids, here we have free air, gasoline, and salt water. Every interface is a key point. So this is the first interface, this is the second one. Here is between air and gasoline, while here we have gasoline and salt water. So this is point number 1, this is point number 2, and the exit is point number 3. As I mentioned, in pressurized tank, the pressure at all these points is the same, and it's equal to P1, the pressure which is shown by the pressure gauge. Okay, so at point 1 we know the pressure, and another point is when you have a free surface, when you have a free surface or interface in tanks, these tanks are assumed to be large enough, so the elevations are constant or steady, and it means that the velocity on the interfaces is 0. So for example, in this problem, at point 1, we know pressure equals P1 and velocity is 0. And the same for point number 2, velocity is 0. So we only have velocity at point 3, which is the exit. Okay, so here we have a fluid flow, so we know that we have to use Bernoulli equation. But to use Bernoulli, in addition to the assumptions I mentioned before, you have to write down the Bernoulli equation in a single fluid. So you cannot write Bernoulli equation between point 1 and 3, because here the fluid will change from gasoline to salt water. So you can write the Bernoulli equation between point 1 and 2 or between point 2 and 3. So know that this is important. And what should we do for this problem? It's obvious that if we write the Bernoulli equation between point 2 and 3, we may find P pressure at point 2, and then we can find P1 because we know the relation between P1 and P2. To find that, it's easy. You just need to write the Bernoulli equation, or just the hydrostatic pressure, because as I mentioned, the elevations are the same and are constant. They don't change. So we can simply start from this point and move towards this point and write the pressure equation, the hydrostatic pressure. So I start from point 1, P1, then I move downward, so I should add the pressure plus gamma of gasoline, gamma naught, times 2 feet. Then I reach point 2 and I can put pressure at point 2, P2. Okay, so I hope I could explain it in a way that you understand what I want to say. Since the interfaces, the level of the interfaces don't change, they are constant, we can use this one. And it's kind of Bernoulli equation. Let me write down Bernoulli equation between point 1 and point 2. P1 over gamma plus V1 square over 2G plus Z1. Because maybe some of the students think that here in this problem we have a fluid flow, so we should use Bernoulli equation. P2 over gamma plus V2 square over 2G plus Z2. Okay, as I mentioned here at the interfaces, we don't have velocity. Velocity is 0, so this term is 0 and this term is 0. And if you put okay, it's not important because you know that here Z1 minus Z2 is 2 feet. So you have this term, and 2 feet. P1 equals P2, and you have to minus 2 feet times gamma. See? And this is gamma of gasoline. So it doesn't matter you use Bernoulli or simply you can use the hydrostatic pressure formulation. Okay, now we know the pressure at point 2. P2 equals P1 plus 2 gamma of gasoline. Okay, now we should write down the Bernoulli equation between point 2 and 3. P2 over gamma, here the gamma is gamma of water, plus V2 square over 2G plus Z2 equals P3 over gamma plus V3 square over 2G plus Z3. Okay, what do we know? We know that V2, I should use the pen. V2 is 0, we know that, and if we put the z-axis here, Z3 is 0 while Z2 is 3.6 feet. P3 is 0 because we are working with the gauge pressure, and here we have atmospheric. It's an exit, it's an outlet. So this term is 0, this term is 0, and this term is 0. We know this term and this term. And what about V3? We know the flow rate and we have the diameter, so we can calculate velocity. V3, Q equals A3 V3. So V3 can be found from if we divide Q by A3. So Q is 0.0 9. Let me check. Yes, 0.09 cubic feet per second, and in the denominator we have pi over 4 and the diameter, which is 0.06 feet square. So we can find V3 31.8 feet per second. Now we can use and we can solve the Bernoulli equation. So P2 is P1 plus 2 feet times gamma of gasoline divided by gamma of water, and V2, this term is 0, Z2 is 3.6 feet equals V3 31.8 feet per second square divided by 2g. Gravity is 32.2 feet per second square. And yes, from this equation you can find P1. You know, gamma of water is 62.4 pound per cubic feet, and gamma of gasoline is 42.5 pounds per cubic feet. So if you put the numbers, you can find P1 equals 746 pound per cubic feet. And you can convert it to PSI. If you multiply this by 1 over 144 feet square over inches square, so you will have 5.18 psi. So this problem is not difficult. Let's move to the next problem. Problem number 98 of chapter 3. Here we have a JP4 fuel. You know, we have a Venturi and a JP4 fuel with SG of 0.77 flows through this Venturi meter. Okay, so we know the gamma, specific weight of the liquid. We know the velocity with a velocity of 15 feet per second. And we know the diameter of the pipe, which is 6 inches. So here we have 6 inches. If viscous effects are negligible, determine the elevation h of the fuel in the opening tube connected to the throat of the Venturi meter. So here we want to find h. Okay, we have this Venturi meter, we have this pipe, we have another open tube here, and we have this open tube here. So we should use these for to calculate the pressure and to find the key points, as it's the first step. I mentioned that where you have these tubes or manometers, you can use them as key points. So here is first point and here is the second point, and I mentioned that you should always go with the flow, so follow the flow. This is first point and this is second point. Let's write down the Bernoulli equation. Do not forget this keyword, sorry. P1 over gamma plus V1 square over 2g plus Z1 equals P2 over gamma plus V2 square over 2g plus Z2. Okay, Let's examine what we know. Okay, we know that if we put the axis here, z1 equals 0 while z2 equals 8 inches. What else? What else do we know? We know v2, velocity at point 2 is 15 feet per second. Remember and be careful, this velocity 15 feet per second is the velocity of the flow inside the tube, inside the pipe, where we have a pipe with 6 inches with diameter, 6-inch diameter pipe. So here the diameter is 6 inches, so the velocity is 15, but here at the throat it's not 15 feet per second, it's more than that. How we can calculate it? Using continuity equation. We know that Q, the flow rate, is constant through the pipe, so A1 V1 equals A2 V2. So V1 equals A2 over A1 times V2. So A2 is pi over 4, 6 inches divided by 12. Oops. Pi over 4 times 6 inches square, and A1 is pi over 4 times 4 inches square, and the velocity at point 2 is 15 feet per second. Here you don't need to convert inch to feet because we have inch in the numerator and the denominator. So from this equation you can find velocity at point 1, which is 33.75 feet per second. As you can see, it's much greater than 15. Okay, so we know this term is 0. We have it, and we have it. What about pressure? You should use these tubes, these open tubes, to calculate the pressure. As I mentioned, this type of manometer measured the static pressure, static head. So for this open tube or manometer, for second point, you can understand that, you can find out that P2 is P2 over gamma the static head equals 6 feet. If you don't know about this equation or get confused, you can use this way. Here is point A and here is point 2. Start from point A, PA, and then you have to move downward. So you should add the pressure, the hydrostatic pressure, so 6 feet times gamma, and you reach point 2 equals P2. So as you can see, P2 equals, and you know that here we have open manometer, open tube, so here we have atmosphere, so PA is 0 because we are working with gauge pressure. So P2 is gamma times 6 feet, so P2 over gamma equals 6 feet. Let's do the same for point number 1. Here is B and I start from point 1 because it has higher elevation. It doesn't matter, you can start from point B. So P1 plus H, because I should move downward, plus H times gamma, and then I reach point B, and as you know, point B is atmosphere, so PB is 0. So P1 equals minus H times gamma. Okay, now you can put the values in to the Bernoulli equation. P1 over gamma. Okay, P1 over gamma minus H gamma over gamma plus V1 square. V1 is 53.75 feet per second over 2g, 32.2 feet per second square, plus Z1, which is 0, equals P2 over gamma. P2 over gamma is 6 feet. 6 feet plus V2, 15 feet per second square, or here we have square, divided by 2g, 32.2 feet per second square, plus Z2, which is 8 inches, so 8 over 12 feet. And from this equation you can find H, which is 7.53 feet. See, it's simple. If you know how to deal with fluid mechanics, you can solve all the problems. Let's go to the next problem. Problem number 118 of chapter 3. Here we have a conical plug which is used to regulate the airflow. So here we have air from the pipe shown in the figure below. The air leaves the edge of the cone with a uniform thickness of 0.2 meter. So here the thickness is 2 centimeters. If viscous effects are negligible, key word for Bernoulli equation, and the flow rate is this much, determine the pressure within the pipe, pressure here. So in this problem, first things first, the first step was identifying the key points. So it's obvious that here should be 1 point, because we should find the pressure within the fluid, within the pipe, and the exit should be the second point. An important point is many of the students confuse when see this figure. It's not 2D, guys, it's a 3D cone, so we don't have two exits. If you look at this, for example, if you look at the system from, for example, left or right, you will see this is the coin and we have airflow. So this is an exit. We don't have two exits or something. So here we have a 3D cone and a 3D system. So it's easy now. Let's write down Bernoulli equation between point 1 and point 2. P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. Okay, what do we know? In these cases, we consider, here, for example, we have exit, and it's a whole circle. So if we want to consider an elevation for this exit, we should use the middle, because we have an exit here, 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 here. And when we do the integral, the elevation, the average elevation should be at the middle. So here is z2 and here is z1. So z1 equals z2. Again, we have exit, and it's a 3D exit. So the average elevation of the exit should be at the middle, at the central, at the axis. It's better at the axis of the pipe. Okay, z1 equals z2, and we know at the exit we have atmosphere, so P2 is 0. What about velocity? We have thickness, and we want to find P1, yes? Yeah, we want to find P1. So we want to find P1. So this term and this term are cancelled out, and this term is 0. We know the flow rate, we should use it. We know that Q equals A1 V1 equals A2 V2. Okay, for point 1, V1 equals Q over A1 equals 0.5 cubic meter per second divided by pi over 4, and the diameter 0.23 meters square, so V1 equals 12 meters per second. For point 2, V2 equals Q over A2. But what is the area at the exit? It's a circle, and we have this thickness, so you should calculate the circumference of this circle and then multiply that by the thickness. Equals 0.5 cubic meters or per second divided by the area is the circumference of the circle, the base of the cone, multiplied by this thickness. This is the area through which we have outflow. The circumference is 2 pi r, because we know the radius, 2 pi r, and we should multiply that by the thickness, h. So it's 0.5 cubic meters per second. 2 pi r is 0.2 meters, and h is 0.202 meters. So velocity is 19.9 meters per second. Now we have everything, and if you put the values in the Bernoulli equation, you can find P1. So P1 over gamma plus V1 square over 2g equals V2 square over 2g. If you multiply both sides by gamma, you will have P1 equals 1 over 2 rho V2 square minus V1 square, because gamma is rho g. And I factor out 1 over 2 rho. And now you have everything. 1 over 2 density of the fluid, of the air, 1.2 kilograms per cubic meters, and velocity is 19.9 square minus 12 square meter square per second square. So P1 can be found as 155 Newton per square meter. And this is how you should solve this problem. I think we have another problem. Yes, let me check. Yes, here is another problem and we should solve it. Problem number 132. Here we have a gate. It's open and water flows under it. Where the depth of the water is 6 feet, and here at the exit the depth is 1 feet. We know the angle of the gate, and we know that the gate is 8 feet wide. So in the third dimension we have the width of 8 feet, and we want to find the flow rate. So it's pretty simple. First things first, identifying the key points. So this is the flow direction. I mentioned that any interface, any free surface is a key point, is one of our important points. So this is the first point, and here we have another free surface, the second point at the exit. So we know our key points. Now we can write down the Bernoulli equation, P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2. Now let's see what we know. Both of these points are free surfaces. So P1 equals P2 equals 0 because we have atmospheric pressure. And the elevation is known. Z1 is 6 feet while Z2 is 1 feet. A velocity at point 1, we should find it because it is not a big tank or something. It's a gate. So water can have velocity at point 1, and you can understand it from here. So this term is 0, this term is 0, and we know Z1 and Z2, and we want to know velocities. So here, since it's not an infinite reservoir or tank, we should find velocity V1, and we should find the relationship between V1 and V2. And as you know, Q flow rate is constant, so A1 V1 equals A2 V2. So V2 equals A1 divided by A2 times V1. A1 is 6, here this is the area, this depth times the third dimension. So 6 feet times 8 feet W, while A2 is 1 feet times 8 feet times V1. So now we know that V2 equals 6 times V1. And now we can solve the Bernoulli equation. If you see V1 square over 2G plus 6 feet equals V2. V2 is 6 V1 square over 2g plus 1 feet. So you can solve this equation. G is 32.2, and by solving this problem you can find V1 3.03 feet per second. Now you can calculate flow rate. Q is A1 V1, so 3.03 feet per second time area, which is 6 feet times 8 feet. So the flow rate is 145 cubic feet per second. So here we solved all the problems available in assignment C, and I hope you enjoyed it. Please solve all the equations, all the problems yourself. Do not see this video and then say, okay, I know it. You should try to solve these. You should try to solve these problems yourself. And in the next video, we start. I think it's about assignment D, which is about chapter 5. Yes, chapter 5 of the Fluid Mechanics 1, which is about energy equation. Okay, thank you for watching this video. If you like this video, or if you're interested in CFD, please like these videos and share our videos with your friends. Do not forget to subscribe to the channel. Thank you for your attention. Thank you for watching this video. Until the next video, take care of yourselves and bye bye.